High-performance computing is getting more complex every day. This is due to the heterogeneous nature of the system. It may contain multi-cores, GPGPUs, mini-cores, burst buffers, persistent memory stores, and all this leads to the MPI per core model that we currently use might not yield the best performance going forward. Up to now, we have viewed the model of the computer for high-performance computing as resource agnostic, but this has all changed. There exist hierarchies of restricted and limited memory, high latency and low bandwidth connections for non-traditional HPC components, interconnect link saturation by the number of connected computational units. And this requires explicit description of the fine and coarse-grained parallelism. All this transforms a complex software development task into a formidable Herculean task. To understand the impacts of the changing face of high-performance computing, let's look at an example. Titan, one of the world's fastest supercomputers, located at Oak Ridge National Lab. Overall, there's an order 5 magnitude difference from computation to storage. Putting this in perspective, we could write out 1 in every 100,000 time steps, or we can write out every other 100,000th value per time step. Therefore, the ability to compute is growing significantly faster than the ability to transfer. And the ability to transfer is growing at a significantly faster rate than the ability to store and read. This has a significant impact on scientific analysis and visualization. The dominant post hoc analysis and visualization paradigm is as follows. Simulations write files, and specialized analysis and visualization applications read files and compute results. At extreme scale on large HPC systems, it's slow to write data. There's not enough space to store the data, and it's very slow to read data. In contrast, the in situ analysis and visualization paradigm is as follows. Spare some supercomputing time to intelligently process, structure, reduce, and analyze. These impacts require new research and development in scientific analysis and visualization. For post hoc paradigm, we'll be looking for more memory-conscious algorithms and new highly scalable algorithms that take advantage of emerging new trends in hardware. Examples of these are out-of-core analytics that use SSDs or burst buffers, or heterogeneous analytics leveraging GPUs, FPGAs, and other accelerators. For in situ, we want to make code instrumentation and analysis development easier. We want to leverage the improved algorithms of the post hoc paradigm, and we need resilient software engineering to perform gracefully when failures occur. The overall goal of in situ is to move from producing a priori products to delivering intermediate explorable products that enable scientific discovery. For Kitware and our collaborators, it starts with VTK. VTK is an open source scientific visualization toolkit. And recently, VTK has undergone a major rewrite of the rendering code, mainly the geometry and volume rendering, taking advantage of the modern programmable GPU and migrating from fixed pipeline to buffers and GLSL. This new work leads to performance, scaling, and shiny new pictures. VTK was CPU bound and now is GPU bound. For geometry rendering, it's 100 times faster, 10 times faster for the initial frame. It uses half the memory footprint, and it's able to do 200 million plus triangles on a single laptop to node on a supercomputer. For volume rendering, it's 2 times faster and improved parallel performance. And there are other highly scalable algorithms like contouring, glyphs, imposters, and Gaussian splatting. And from VTK, we get ParaView, an open source, multi-platform analysis and visualization application for analyzing extremely large datasets using distributed memory computing resources. ParaView is a client-server application. It has a data server for computational intensive algorithms. It has a rendering server that can possibly leverage additional visualization resources. And it has a client for control, display, and rendering of small data. And ParaView provides scalable, post-hoc scientific analysis and visualization to tens, hundreds, or thousands of scientific and engineering simulators. Inside the ParaView framework lives ParaView Catalyst, the in situ analysis and visualization framework. To utilize ParaView Catalyst, a simulator is instrumented with Catalyst, and an adapter is created that maps the simulator data structures to the VTK data structures. The production-ready ParaView Catalyst has been shown to have small runtime overhead on a simulation. And in addition, it's a faster time to solution than the post-hoc paradigm. And ParaView Catalyst has been shown to scale to 1 million MPI ranks on Myra, an IBM Blue Gene Q at Argonne National Lab. Catalyst is capable of producing multiple output types: static images, explorable images, charts, geometry extracts in a number of formats, ASCII output of single quantities and statistics. And for portable data parallel algorithms, there's VTK-M. VTK-M allows you to collaborate, contribute, and leverage threaded algorithms. The algorithms run on all next-generation hardware, and the data parallel primitives provide the abstraction layer to this hardware. VTK-M is a write once, run everywhere framework. It utilizes a portable control environment and execution environment, and this is accomplished by a device-dependent device adapter, which allocates memory, transfers data, and schedules the work to be done. The VTK-M architecture combines the strengths of multiple projects: EVO from Oak Ridge National Laboratory, DAX from Sandia National Laboratory, and Piston from Los Alamos National Laboratory. It's a layered architecture with data parallel algorithms, an execution environment, and arrays on the bottom level. On top of that lives worklets in the data model that can be accessed by in situ applications. And on top of that are filters and a data model more appropriate to a post-hoc paradigm. And VTK-M algorithms have been shown to outperform MPI per core algorithms. This has been demonstrated on isosurfaces, volume rendering, ray tracing, and mesh simplification. These solutions, in their various stages of development, place Kitware and our collaborators down the road to exascale computing.